everyone, we're back with the fourth episode of Farming Fast and Slow with Adam Wolf. I am co-hosting again. I'm Jess Bollinger. And just a reminder about the schedule for today. We are going to do about 30 to 45 minutes of discussion, followed by 10 minutes of question and answer. If you have questions, you can submit them below on the bottom of the screen using the question and answer button. The webinar is being recorded, and we will circulate the recording on our YouTube channel, on our website, and also via social media tomorrow. So with that, I'm going to turn it over to you, Adam.
Jess, thank you. It's interesting to think, where do these topics come from? I found myself earlier today wanting to do a whole episode on the saturation vapor pressure curve. It's a fascinating part of agriculture, but actually today's talk is, on the surface, it seems kind of obscure, vegetation spectroscopy, and yet it doesn't really cover anything that different from what our eyes can see. And so there's just some aspects of it that, we can bring some quantitative measurements to bear to understand, what's going on in these fields. And obviously one of the benefits of having this digital eye out there is that we don't have to literally go out there. And so, a machine can measure day in, day out. Satellites are rotating around the Earth. And, one of the kind of goals we have here at Arable is to be able to take these same measurements on the ground and relate them to that thing up in the air. And it was kind of funny. I didn't really realize it, until I was preparing for this talk. It's funny, as you get older, you reflect. I earlier was working on, satellites looking down at Earth. And now we've got this, device on the ground with this spectrometer looking into the sky. And I realize I've seen clouds from both sides now. And now it all just came together, for me. So anyhow, I'm going to share this presentation. It'll be available afterwards, but figured I would kind of go through some slides of theory. And then we can figure out, okay, well, what makes this relevant to agriculture? Can I farm better because of this? Can I find problem spots? Can I do yield prediction? All these concerns about, being a business person engaged in agriculture, this has some impact. But let's just start in on the technical side.
Sounds great. I was wondering if you could possibly just cover what is spectroscopy, or, starting from the beginning.
Yeah, and while I do that, maybe the host can enable attendee screen sharing. So spectroscopy is a way of breaking apart the color spectrum from this, what we see as panchromatic light into its individual components. And then when we're thinking of it, what's the difference between a spectrum and spectroscopy is, this idea of quantifying or measuring it, using it to, make some inference, like, seems like there must be plants down there, right? And it's actually a pretty interesting exercise. You can go to publiclabs.org, I think it's called, and they'll sell you a little kit that consists of a piece of paper, a DVD, and there's not even tape involved. So you can end up taping a little kind of box around the camera of your phone. And there's this DVD in there. And so what do you know from looking at a DVD is it's, it's kind of silver, but it's colorful. It breaks up the spectrum. And what's going on in there is it has all these little prisms. And so you can aim that spectrometer, okay? So spectroscopy uses a spectrometer and aim it at some light. And if you look at, you know, an LED bulb or a fluorescent bulb, you're going to see little areas of brightness in exactly the part of the color spectrum where those lamps are emitting. Okay, so
what's the difference between a spectrometer and a camera?
so a camera is like a spectrometer. It has these RGB channels, RGB standing for red, green, blue. And you can use a camera as a spectrometer. And people do this. There's a phenocam network that's used. One of the obstacles, though, is that you know, the objective of a camera usually is to present an image for the human eye to consume and appreciate, not for, you know, a machine to make an inference. And so in order to do that, there's a lot of brightness compensation that goes into it. So, you know, my phone has a nighttime mode. You know, old mechanical cameras have an aperture where you can control the amount of light coming in. So there's some amount of brightness control, and then a digital camera also has some white balance.
Like the HDR that you'll see on all the cell phone cameras today.
Well, the HDR is something different, is a high dynamic range.
Okay.
Okay, so white balance might be, you know, I'm lit by artificial light right now. And if I go outside, I'll be lit by the sun. You know, if there was some, you know, old fluorescent bulb in here, I would look kind of blue. And the white balance kind of takes into account the ambient lighting in order to kind of normalize it. And in fact, the mark here more or less has the same phenomenon, which is that it's measuring the downwelling light in order to interpret the upwelling light. So, you know, a lot of times, do you remember that dress? There's a controversy of like, do you see gold or do you see blue here?
Oh yeah, the two colors, and people saw opposite colors.
People see different things. It's the brain is interpreting, well, what is the ambient light in order to figure out what is the spectrum of this reflected light.
Got it.
So your brain is like doing all this compensation on its own to kind of factor in the ambient conditions. But when we do these interpretations, often we're looking at a surface and we see the reflected light. We want to know what is the spectrum of that reflected light. And if it happens that the incoming light is totally wonky, if we're in, you know, a greenhouse with a sodium lamp, it's just going to have a different spectrum. It's going to be, you know, more orangey, you know? And so
when satellite, how do you possibly get the ratio? Is it just the same concept where they have the bands on both sides or something like that? Because it's also rotating.
Well, and you're right that the angle that the light comes out also matters. So different surfaces, you know, some are reflective and some are kind of matte surface, and so they do sort of different things to the light. And so you might interpret like, how bright is that surface? What's its intrinsic reflectance? Kind of depends on what angle you're looking at it and what angle the light is coming in. So this light that's coming in and bouncing off my computer, you know, this side of the computer looks brighter than this other side that's not receiving the light, but it's the same material, you know? And so definitely the ambient light, the angle it's coming in, the angle that we're looking at it, all goes into this interpretation. Cameras are, you know, ultra sophisticated. Obviously, you know, Instagram, all these things, it's like a multi-billion-dollar industry. So there's a lot of effort that goes into computational photography. And there's some super interesting cameras that are doing this. I mean, this camera has 2 cameras and a spectrometer on it. And the 2 cameras, one is wide angle and one is telephoto. And so, you know, once we get into, you know, smartphones, there's a lot of complicated stuff, but the, you know, the basics are there that, you know, light is coming in at all wavelengths, and we can sort of create a spectrometer which splits that light with a prism or just filters that light in order to measure it at individual wavelengths. And then for us, we measure a voltage and record it. And there's really not a lot of difference for, you know, in the wide world of spectrometers, they all kind of work that way. With details as far as, you know, what's the sensor array and, you know, what's their spectral resolution and whatnot. But, you know, so this is all, I don't know, we're talking about the broad world. And just it's relevant to know that, you know, our eye can look at dirt and recognize it's dirt, not because it's, you know, got a bunch of grains and some, you know, hay in it or whatever, but because, you know, brown things that are below us are often dirt. And, you know, that green stuff is probably plants. And if it's white on top, it's probably snow. So we're interpreting those colors with our eyes. And, you know, the only detail that the spectrometer does is make it quantitative so that a machine can do that.
And so the number of bands you have is the number of different wavelengths that you can look at. And for us, you know, we do a 6-band spectrometer. I think you can do 128. There's also, what's the maximum number that you can have on a spectrometer?
I don't think there's a maximum, but, you know, the most expensive spectrometers you see might have something like 1,024 bands, 512 bands over some range. You know, so Hyperion was a hyperspectral satellite up in space. Maybe it was, 256 bands, something like that. And then if you've got a great research budget, you can buy an ASD field spectrometer, full backpack thing, and go out. They use this as kind of ground truth for Avarice, which is a NASA plane. And the ASD spectrometer has, you know, something like 1,024. And so that sort of relates to the sensor array and the beam splitting to, like, you know, spread out the array. And, you know, there's usually some electronics to control the noise of temperature fluctuations.
Like the passive light. What I was wondering is if when you have that many bands, you know, what are the more interesting things you can do? Is it that you're looking at nutrition in different crops, or when they're out there, what is it that they're ultimately sensing with that type of equipment?
Well, different parts of the spectrum, and we'll look into this a little bit, different parts of the spectrum have kind of different features. And so when we think of the visible parts of the spectrum, you know, right now it's spring. I'm seeing a lot of blossoms out there. So some are pink, you know, those are pigments. Maybe there's some leaves in our Japanese maple that's coming out. Those are kind of reddish. Then there's a bunch of, you know, young leaves. Those are like pale green. And as they mature, they're getting dark green. All those are pigments that our eyes can see. Okay, so that puts them in the visible spectrum. Then there's stuff that's in the spectrum that we can't see. And this might be called the near infrared or the shortwave infrared to distinguish it from the thermal infrared. And, what has features out there? You have things like water vapor absorbs at, 950 nanometers and 1450 nanometers. And then the dry matter of a plant absorbs out there. And as well, there's, soils and soil minerals in particular have a huge, diversity of different absorption features. So you could actually go, it's a pretty fascinating data set. You can go to the Jet Propulsion Lab has a spectral library, and it's got like 50 different soils that were captured, and they were used to try to identify, like, can we see gypsum, which is like white dune sand, and can we see black soil? Some man-made materials, can we see asphalt and concrete? What's crazy is that there's a huge variety of space minerals. Can we, looking at moon rocks and things like that, to identify what its composition of, so for a plant, we care about, these pigments like chlorophyll, because it relates to, nitrogen nutrition and photosynthesis. We care about carotenoids and anthocyanin because it relates to stress that the plant has experienced. Soils, are interesting because you might care about organic matter in the soil. Is there a bunch of lignin that's visible?
Yeah.
That you can start to quantify?
I feel like this is really interesting, but it just sounds so scientific, and I'm wondering, how does it get used on a day-to-day basis in everyday farming operations? How do you make this relevant?
I mean, there's kind of a couple really core use cases. The big one is canopy cover.
Okay.
And not just generic canopy cover, but green canopy cover. And we'll get into this in just a minute, but that canopy cover is one of the most, important vital rates of a plant that you can measure, which is, leaf out is important for knowing the onset of phenology. Total leaf area is going to be able to say, well, this part of the field obviously is more vigorous than that part of the field. Sometimes people use this term vigor to reference that canopy cover. The canopy cover determines the amount of light that the plant is capturing. And so if we add up all the photons that, the leaves times the downwelling radiation captured, then, that's going to relate to yield pretty, substantially. So this is kind of one of the big measurements, but, there are operational tools. Green Seeker, I'm thinking Yara has a product that's kind of tractor borne, that they're measuring the spectrum in order to measure the canopy nitrogen content, and use that for a real-time fertilizer application.
I'm wondering though, if I'm watching every day the change in the canopy cover, is it something where it will catch before the human eye that there's decline in the canopy cover? Is it something that, how reliable is it to say we need to go scout these fields in terms of changing the priority of operations in a farm?
Sure. I mean, and in some ways, there's this idea of leading and lagging indicators. So the dream is always to be able to, see something with a spectrometer that is going to predict problems that are going to be manifest in the future. And, canopy cover is both a leading and a lagging indicator, because it's the result of a bunch of things that happened,
right?
So you can't change the facts that you've got low canopy cover. However, if we take sunlight times that canopy cover to get a photosynthetic rate, that predicts future productivity.
Okay, because that's the limiting factor in how much the plant will grow, how much vegetation there is for it to absorb sunlight.
Absolutely. And so there's kind of this, I don't know, divide in the literature where there's a lot of historically there is a lot of active work using canopy cover as a measurement of the state of the plant. And right now there's a lot of intensity looking at photosynthetic rate from spectroscopy, and some of that is using some exotic measures like fluorescence. Some of it is not that exotic
Mhm.
in terms of what it's measuring, but the overall interpretation is, this is something that is a change that's in the future versus this is like the state of things as it is now. One of the areas that I've always been intrigued by is to what extent can a spectrometer spot a disease or a nutrient deficiency or a nascent issue before the human eye can see it. And
Mhm.
so, a lot of diseases are obviously visible. You've got lesions, whatnot. Maybe you could see the whiteness from a powdery mildew. Those are things that, by the time you're seeing symptoms, the infection happened, a week before.
Mhm.
So is it possible that we can look at particular parts of the spectrum where, let's say, the pigments have degraded and our eye can't see the yellowness, but it doesn't mean it's not suffering?
Got it.
So that could mean potentially, one of the holy grails, I think, is being able to use more preventative sprays instead of curative sprays.
That's what I was wondering, if there's a way to tie it back together so that you get some kind of alert that there's this decline that's been corrected for all the atmospheric interruptions at that time, but then being able to take some action in response to knowing that there was this change or small decline. And I don't know, I guess for me, it's a struggle to, is that something that's possible with NDVI, or is that just something that's, we're not even using yet?
Well, I think we're at the start of an era on two fronts. One is gathering benchmark data for what does good look like.
Mm-hmm.
Like, that's a healthy plant, grew quickly, so the light use efficiency, its ability to turn photons into new biomass is high. The maximum is high, it grows for a while, it senesces. So, this idea of a library of, okay, this is what a healthy plant looks like spectrally.
Mm-hmm.
And then, any candidate plant, we can compare it to the benchmark and say, does this look healthy? And,
Mm-hmm.
we saw that in the last couple of seasons. Like, there was the case of these tomatoes that were hailed out. This is in the
Mm-hmm.
Central Valley, which there's a lot of processing tomatoes. It was hailed out, and then it had a Phytophthora outbreak.
Right. What I'm
And
thinking too about the charts we did with the folks at UNL TAPS, where you could see all the NDVI curves for the different plots. I think there were 16 different plots.
yeah,
And it's, for me, I feel like it goes into, is it that curve at the beginning, or is it that peak that is the indicator of plant performance?
I think it's some of each.
Okay.
So the maximum attained biomass, is probably going to correspond to a higher yield
Mm-hmm.
because it's got more light absorption, more canopy nitrogen storage. Can have potentially grain that's got more protein content. The rate it took to hit that might
Mm-hmm.
matter. The timing that it hits the peak um, seems to correspond to tasseling. So that's like the onset of irrigation in Nebraska. A lot of the diversity, though, was related to the drawdown
Okay.
at the end. So the senescence, that would be an interesting set of curves. I think we should have a session on just spectral phenology at some point, but seeing the differences in those curves drive down, you had, over 2 weeks of difference between the earliest and the latest. And that definitely ties into, let's call it logistics, getting out to the field. When do I need to get out there? Is it going to dry down before the onset of the fall rains? Do I need to invest in propane so we can dry this down? So there's different types of decisions that are happening.
Right. And even if there was a way to tell by that rate of the curve right before the tasseling was going to happen, if I think we saw that everyone who put out fertilizer right before that point did better than the folks that were just doing, it all up front, and the folks that were just doing it intermittently throughout. But the ones that timed it perfectly seemed to have the best yield outcomes at the end. So I'm wondering if it's something like that we begin to, with enough data, that we can say something about.
I mean, synchronizing inputs with plant need is always a recipe for success, so it can be optimized. I'm conscious of the time though, so I wouldn't mind running through some slides.
Okay.
And then, we can follow up with some Q&A and whatnot. So among other things, when we're both talking about figures that nobody else is looking at, it demands. All right, so sharing my screen. This is an example of a mark above a vineyard, and so it's looking down at the ground, and it's got this hemispheric diffuser, so it's measuring light at all angles. Similar to this up top, there's a solar radiation sensor called a pyranometer. It's measuring light at all angles, okay? And similarly from down below. So it's getting this kind of weighted average here, mostly around the vines, but it's definitely picking up some of the cover crops, which, depending on the application, is useful or problematic. And just for reference, this is looking at an area a couple meters wide, whereas satellite like Sentinel would be measuring on the order of 10 meters wide. So this is just this little targeted spot in the middle of a field. Let's see here. So one of the things to get our head around thinking about spectroscopy is what does the solar spectrum looks like? And we're actually making use of these measured and modeled observations of the solar spectrum coming from NREL, the Natural Resource National Renewable Energy Lab. There's 2 NRELs in Colorado, which causes me no end. And so we're measuring with these 1, 2, 3, 4, 5, 6, 7 bands. At that time we had 7 bands. And you could see that it's roughly corresponding to, most of them are in this visible and a little bit in this near infrared region. You notice that the sun is very intense here in the blue. And what a surprise when we look up, we see a lot of blue light out there. And the units here are watts per meter squared per nanometer. So watts per meter squared is like, the energy, falling onto some area by, solar radiation. We might use these units. Mm-hmm. And then per nanometer is, we're discretizing. So if we add up all the energy per each of these nanometers, we get the total solar radiation. And now let's look at the leaf. So the leaf is basically black in this visible spectrum, where the absorption is, 95% in most of it. And there's a little bit less absorption here in this green part of the spectrum, and that's why plants look green. Your eyes, by the way, have their own spectral sensitivity. And so you don't see necessarily just the average of this color. Your eyes are a little bit more sensitive here in the middle and a little bit less sensitive, obviously, at the edges. So then the solar spectrum, or the leaf spectrum, goes up very steeply right here at this place that's called the red edge, and it absorbs almost no light. And it's nearly transparent. So, if you think about looking into a cupboard, in the visible spectrum, a leaf is like looking at just an opaque, mug. Whereas in this NIR part of the spectrum, it's like looking through these clear glasses. There's a little bit of absorption. You can't see through, too many layers of glasses, but they're pretty see-through. And then these other features, we talked a little bit about these like water features and cellulose features, have these impacts on the shape of the spectrum, and we can interpret those. So, what does chlorophyll do to the leaf spectrum? Okay, so it's impacting basically this range in the visible, and it's avoiding or it's not absorbing light out here in the near infrared. And my interpretation of that is, plants are harvesting light so that they can grow, the photosynthetic electron transport, but too much light, they have to deal with it. They have to get rid of water in order to stay cool. And so they've got this red edge, so they're absorbing the light that they can use and avoiding absorbing the light that they can't use. And here you see that the chlorophyll is extremely absorbent out here in the blue, and it's much more weakly absorbent in the green, which is why we see the green. It's not absorbing as much light. It's absorbent again here in the red, and then it drops off again. And so it just kind of works out that the best places to measure chlorophyll are not at these places where it's the most absorbent, and it's not these places in the NIR where it's not at all absorbent. It's places like the green or the red edge where it's weakly absorbent. And so we have sensors that are used, in our case in the green, to measure the chlorophyll index using the reflectance here compared to the reflectance over there. So carotenoids, these are, tomatoes, carrots, some of your, fall colors. These are the kind of yellow-based reds is how I think of them. Mm-hmm. And they absorb, well, they're more weakly absorbent in here in this 530. It's kind of a blue-green. And so often the 530 and 570 are used as a way to measure the carotenoids. And carotenoids are, they call it the sunscreen of the plant. So plants are playing with the carotenoids when, they're getting more light than they can really make use of. And so it's kind of a protective pigment. Anthocyanin, now these I think of as like these blue-based reds. So this is a Japanese maple, and often the calculations are measuring green versus red or green versus blue, because you can see that varying the anthocyanin causes variation in the reflectance in this blue and green, you can see over here, or green and yellow, but really has no impact on the blue and the red. So that's a leaf. So it's relevant to understand, okay, well, if we sampled a leaf, and you could do that, put a little clip on a leaf and measure the chlorophyll content. These guys at Michigan State Photosync have a measurement that does that. A SPAD meter does that. So there's ways to measure the nitrogen status of the plant with just the leaf, but we're up above. Okay, so we're not looking at just the leaf. We're looking at this mix of soil and leaf and shadow, as it turns out. So this is the same patch of grass looked at where the sun is on the left. It's on the far side of me, so it's casting shadows. And I am looking at those shadows in addition to the leaves. And on the right, the sun is at my back. Identical patch. And so what's interesting is that, if we blur our eyes, then we get, the difference. What is a satellite see versus what is, a camera see? And so really this is like what the, what a spectrometer sees. The mark sees this average. Okay, so it's averaging the leaves, the soil, the shadows. If there's non-photosynthetic vegetation like straw, bark, all that stuff is showing up in this image, and we're measuring the average. So, one of the challenges of remote sensing science is this unmixing. How do we take this one pixel, extract all the different constituent colors, and see what ingredients went into making it? Okay, and that's where vegetation indices come in, where they're ultimately, trying to make some estimate of how much leaf versus soil there is. And so in the following slides, I'm going to give you sort of a set of canopies that vary in terms of their leaf area, their soil brightness, the chlorophyll even. And so here, this brown line, that represents a soil spectrum with no leaves. And then we're adding in these little increments of leaves, starting with this lightest gray line. Okay, and if we go down here, I'm increasing the LAI from none up to 4 meters squared of leaf area per meter squared of ground area. And initially, each new leaf is covering up a totally new piece of ground. And so it's having a big impact on the apparent brightness. And so these lines are very far apart. And so we're adding more leaves. And at a certain point, each additional leaf, it's covering up probably mostly other leaves and maybe a little bit of soil. So it has this saturating effect. And the reason why people have these different spectral indices is more or less to deal with the saturating effect. So here there's the enhanced vegetation index, the modified soil adjusted vegetation index. All of them are strategies for either bringing in other spectral bands or modifying the math in some way to extract more dynamic range. It's like your HDR camera.
Got it.
So this is like the basic picture. What's crazy is that actually that, constant soil line is really high if it's wet, and it could be really low if it's dry. It could be, an alpha sol, kind of reddish, like they have, maybe in the Southeast, ultisols, or it could be, mollisol like they have in the Midwest, dark brown. So there's just this huge diversity of soils and soil colors, as well as the organic matter content, so humus makes it darker, and soil moisture content, which, is going to make it darker. So there's this unknown soil brightness that goes into interpreting this leaf area index. Mostly ignored because you got no idea what it was. And so here, this is just kind of randomly choosing different soil brightnesses. You see, if you're almost all leaf, then soil brightness doesn't matter because you're not seeing any soil. But down here at, let's say, canopies that are only moderately full, there's huge impacts of soil brightness on the vegetation index. And so one of the
reason to unmix it would be so that it's not brown leaf, but to know that it's brown soil.
Right. Well, brown leaf, I'll show you in a couple of slides, is kind of lack of chlorophyll.
Okay.
That has a slightly different impact because if we go back a couple of slides to look at the chlorophyll, brown leaf, if we're measuring NDVI using this red band and this near infrared, brown leaf means that this band is changing. It's becoming less absorbent. And so if it actually is senescing with the same amount of canopy cover, that lowers the NDVI as well.
Got it.
So the soil has an impact where, ultimately this is saying, gosh, I don't know if I have 0.3 units of LAI or 0.7, factor of 2 in terms of how much biomass. So this is an interesting one, leaf angle. I went deep into leaf angle during my dissertation. What's the difference between a corn plant and a soy plant and a wheat plant and a canola plant? Is NDVI identical for all of these? The issue is that, some of those plants, like a wheat plant or a corn plant, the leaves are fairly erect, is called erectophile. And then if you take, I don't know, sunflower, soybeans, they're kind of flattish, which is called planophile. Mm-hmm. And so this leaf angle, actually this is not LAI, it's leaf angle. If they're basically vertical, you see a very different absorption of light versus when they're more or less flat. So that has an impact.
Do you have to correct for it when you're looking at the two different types of leaf angles based on the crop?
Yeah, so if you're going to come up with, I think you have so many, kilograms per hectare of biomass out there, it more or less means that it has to be crop specific to deal with this leaf angle thing. And to a lesser, probably not lesser extent, there's also the impact of the row spacing, so if a corn plant is on, 30-inch centers, and then, lettuce is on these 60-inch beds with the furrow, that affects the clumping, where just intrinsically some crops can be very dense, but there's still a lot of furrow visible. Mm-hmm. So addressing that also shows up as important. And here's this senescence that I was showing you. So here's a simulation where we're showing the leaf area is increasing while the chlorophyll is decreasing. So if we go to this part of the curve, It's the second half, you know, the growth phase, it's increasing in chlorophyll and leaf area. It's not totally visible here, but, you know, common sense says that, you know, it's growing here and then it's declining over here. And as it's declining, there's still a lot of biomass in the form of leaves. They're just translocating all of the chlorophyll as nitrogen into grain protein. This happens to be a soy crop.
And that's when the leaf changes color from green to a yellow and eventually dies.
Yeah, exactly. Green to yellow to brown. You know, maybe there's a forced defoliation in the case of potatoes. So that's all going to be visible. And here, this red line is our NDVI. So it's interesting. This is increasing, reaches a maximum here at around 2. And then the chlorophyll is going to nothing as it keeps going higher. And then it drops off. So this says, gosh, with NDVI, I don't know if I'm looking at a full canopy, 4 leaf area units with no chlorophyll in it, or a juvenile canopy with a half leaf area unit and chock full of nitrogen. And so that's where we get the ambiguity of interpretation that is the essence of remote sensing science is, okay, well, what do I do to determine if I'm in this state or if I'm in this state, you know?
Right.
These flat lines are some simulations we did using a different spectral band, which wasn't as sensitive to chlorophyll. So they don't diminish in the absence of chlorophyll. So that's maybe useful as a senescence measure. Yeah. Or we could do a more complicated retrieval where instead of just this, you know, relationship between leaf area or the NDVI and leaf area, we've got, you know, a retrieval that includes, you know, extracting the chlorophyll out as well. And so this becomes where it's most interesting. Why do we have, you know, 7 spectral bands here, 6 spectral bands? It's to be able to do these kind of more complicated retrievals.
Right. And it feels like this is the beginning of a number of interpretations that has to happen before it's completely usable on a farm, just because I feel, you know, if you're trying to make decisions quickly, sitting down and interpreting all these graphs is time consuming.
Well, for sure. And there's parts of it that you just kind of have an overall impression of, like it's growing, it's senescing. Maybe that's useful for, you know, synchronizing your sense of the biological clock. But if you wanted to get to the point of like, on what day will it achieve 10% moisture content, that's where this, you know, quantitative interpretation is. What's the literal pounds of nitrogen per acre I have in this canopy right now? And is that enough to meet my yield objective, you know, as measured in, you know, late June? You know, so that's where, you know, quantitative answers, you know, the most useful stuff is obviously quantitative instead of qualitative. And, you know, the reality is that they all are kind of crop specific. You know, and I think the people who've really gone deep on things like this, like, you know, Yara has a handheld probe for measuring the canopy nitrogen. It's based on thousands of trial plots, you know, for all different crops. And so that's where some of the, you know, complexity comes from, you know, having a measurement device versus a total, you know, productized solution decision support, is that investment in the agronomic research. I saw that we had a couple questions come in though, so should we?
Yeah, I was going to read them. The first one is from Felix. He wrote, "Hi, Adam. Do you think that we can use the mark to take measurements of nutrition in barley as we do with a SPAD, SPAD, or green seeker? Is it possible to get the same index?"
Yeah, so the answer is yes. We're focused on using the green chlorophyll index for doing that. We have done some work in corn for measuring canopy nitrogen using this. One of the kind of obstacles for me has always been, you know, the use case. So I remember talking with Nutrient Star a couple of years ago, which is kind of a public sector program that evaluates, you know, nitrogen decision support. And, you know, it alerted me, you know, to the reality of it's okay to make a measurement device, you know, that's helpful, but it doesn't get us all the way there. And often nutrient decision support fails because, you know, by the time you need it, the data is maybe obsolete. And so I think we have a niche here is in being able to, you know, make things, you know, it's continuous in the field. And so it's able to have a measurement that's as, you know, current as today. Potentially we could combine that with, you know, imagery to have a recipe for the whole field. But nonetheless, that calibration work is just absolutely critical. So that's the next step.
The next question is, what is the benefit of having this device close to the crop versus getting a full field picture from a satellite? Is there an advantage or disadvantage to either?
I tend to think in some ways that there'd be an advantage to being higher up. You know, so it's representing more area. So that's great. You know, just think like sampling error goes down as you're measuring more. You know, the benefit from being closer is maybe, you know, you've got some small plot that you want to know, okay, what's happening in this treatment versus, you know, a neighboring treatment. And then there's like logistics. So not a lot of people have, you know, 30-foot poles that they want to manage. So in general, though, I would tend to think that the, you know, higher might be better. And we're exploring, you know, what if this is off to the side of the field, looking at it at an angle, which, you know, some assumptions would have to be made as far as what the solar spectrum is and this type of thing. But there's, I think, some real potential there.
Great. I believe those were the questions we had today. And Adam, we're, I think, quite a bit over on time. So maybe I can wrap up with a couple housekeeping items for next week. Adam, you said that the presentation is going to be available to the attendees. You're going to, I guess, maybe circulate via email after the talk today. Sure. Cool. And then the second thing is we have another special guest next week, and we will be talking about breeding and future of food in restaurants and the breeding pipeline that goes into making that food. So we're excited to have our guest for that.
Not enough is made of the importance of food tasting good. So I can't wait.
And we'll be sending an email with the registration link for the next episode tomorrow. So more on that soon.
Love it. Can't wait.
Thanks, Adam.